Hello everyone, I am Varsha. Today I will be discussing about review on theory of computation. So I will be discussing about introduction, key concepts in automata theory, complexity theory, types of automata, application of theory, and conclusion. So coming to the introduction, the theory of computational deals with how efficiently problems can be solved on a model of computation using algorithms. It mainly concerns itself with three branches, that is automata theory, computability theory, complexity theory. So in automata theory, it studies abstract machines, automata, and the computational problems they can solve. In computational theory, in computability theory, it determines what can be computed and the limitations of different computing systems. And in complexity theory, it examines the resources, that is time and space, needed to solve a computational problem. In automata, concepts in automata theory. Finite automata. A finite automata is automata with a limited number of states. First is deterministic finite automata, DFA. It gives a specific input and a current state. There is exactly one next state. In non-deterministic finite automata, NFA, for a given input and state, multiple next stages are possible. For example, a simple text search algorithms uses finite automata to match patterns in strings, example finding a word in a document. Language recognition. Finite automata recognizes regular languages. Coming to transaction function. It defines how an automata moves from one state to another based on input. A mathematical representation. It can be mathematically represented in this way, where this is the transition function and q is the current state, a is the input symbol, and q dash is the next state. For example, in a vending machine, the state transition from waiting for a coin to coin inserted upon receiving a coin. So coming to real world application of automata, it is used in compilers to break source code into tokens and finite automata model protocols to ensure proper communication between systems. Coming to complexity theory. Complexity theory is concerned with classification computational problems based on the difficulty and the resources needed to solve them. So time complexity, the amount of time an algorithm takes to solve a problem relative to the size of the input. The classes of complexity, P, that is polynomial time, problem solvable in polynomial time. Example, sorting algorithms like quicksort. NP, non-deterministic polynomial time, that is problems for which solution can be verified in polynomial time. Example, Sudoku or traveling salesman problem. NP hard or NP complete, the hardest problem in NP. If one NP complete problem can be solved in polynomial time, all NP problems can be solved. For example, solving a Sudoku puzzle in NP because checking if a solution is correct can be done quickly, but finding a solution may take a long time. Coming to space complexity, the amount of memory required by an algorithm. A problem solvable using polynomial space. For example, solving a chess game using brute force involves exploring all possible moves, which can require significant memory. So, applications of complexity theory, that is, it relies on hard problems like factoring large numbers that are infeasible to solve quickly, ensuring data security. AI algorithms often deals with NP problems where finding efficient solutions or approximation is crucial. Computability theory. This branch of computation theory deals with what can be computed in principle and what cannot. Turing machine. Introduced by Alan Turing in 1936, a Turing machine is an abstract computational model that can simulate any algorithm. It consists of a tape, a head, and a set of states. a tape that holds symbols, a head that reads and writes symbols on the tape, and a set of states that determines how the machine reacts to the symbol. For example, a Turing machine can simulate a basic calculator solving arithmetic problems by following set of instructions. Undecidable problems. Some problems like halting problem cannot be solved by any Turing machine. The halting problem asks whether a program will stop or run forever. Turing proved that no algorithm can decide this for all possible programs. Recursive function. Functions that can call themselves as a part of their execution. Computability theory explores whether certain functions are computable and which are not. For example, a recursive function to calculate the factorial of a number is computable, but finding a general algorithm to solve all instances of the halting problem is not. Types of automata. Finite automata types are DFA and NFA. Coming to DFA, exactly one state for each input symbol, and NFA can have multiple possible next states for each input. Application is regular expression, text searching, and traffic light system. Push-down automata. It includes a stack which allows it to store additional information. Language recognition. It recognizes text-free languages used for praising nested structures like parentheses in programming language. For example, a PDA can recognize if parentheses are balanced in a string. For example, both brackets open and bracket close is valid, whether one bracket open and one bracket is not closed is not. Linear bounded automata. Turing machine's variant, it operates within a limited region of its state. Language recognition, it recognizes context sensitive languages, and application, it describes more complex languages that can go beyond context free languages. Turing machine, most powerful machine model, can simulate any algorithm and recognize recursively enumerable languages. Application is Turing machine form the theoretical basis of modern computing system. Application of theory of computation. First is artificial intelligence. Automata and algorithms derived from the theory of computation helps in decision-making processes, pattern recognition, and AI models. For example, game-playing AI like chess engines use complex algorithms based on automata theory to determine the best move. Second is machine learning. Complexity theory helps in understanding the computational limits of learning algorithm. For example, finding the most efficient way to classify data can be modeled in NP-hard problems, leading to heuristic solution. Data analysis. Automata theory is used in tools like regular expression, which helps in searching and processing large data sets. For example, web scraping using automata-based models to extract structured data from unstructured sources. Cryptography. Complex theory ensures that cryptography algorithms remain secure by relying on problems that are hard to solve. For example, factoring large numbers. Coming to the example, RSA encryption based on different difficulty of factoring large primes is used to secure internet communication. Internet of Things. Automata theory helps in managing the communication between various connected devices. For example, protocol verification in IoT system ensure that devices communicate efficiently and securely. Conclusion. Automata theory, computability, and complexity are essential in understanding what computers can do, how efficiently they can solve problems, and where the limits of the computation lie. Key contribution are automata theory forms the basis of understanding computational and designing algorithms. Computational theory, it establishes the limits of what can be computed. Complexity theory, it helps classify problems based on the difficulty and resource requirement. Research. With the rise of quantum computing, new computational models are being developed that may break traditional complexity barriers, offering new ways to solve previously unsolvable problems. These are the references, and thank you for watching.